In this video, we will be making a calibration curve in Excel to find an unknown mass fraction. The calibration curve is a graph which gives the relationship between one type of measurement and another. Since the mass fraction, which is a unit of concentration, is related to the density of the solution, we can graph a few data points for solutions for which we know both the mass fraction and the density. We'll be graphing data for 4 different solutions, A, B, C, and D, which each have different mass fractions and corresponding densities. The equation for the line that fits those data points will tell us the relationship between the mass fraction of any fructose solution and its density. If we know the density of an unknown solution, we can find its mass fraction using our calibration curve. Mass fraction is calculated based on how each solution is made. You are weighing out different amounts of fructose for each solution. For example, for flask A, you are asked to weigh out approximately 0.65 grams of fructose. You should report all digits from the digital scale, which in our case reads to 4 digits after the decimal. For example, you might measure 0.6545 grams for flask A. To calculate mass fraction, take grams of fructose measured on the scale and divide by the volume of solution you are making. You are using 25 milliliter volumetric flasks to make your solutions, so the volume of each solution is 25.00 milliliters. 0.6545 grams of fructose divided by 25.00 milliliters gives a mass fraction of 0.02618 grams of fructose per milliliter of solution for flask A. To find the density of a solution, you will take its mass divided by its volume. Make sure to exclude the mass of the glassware used to weigh the solution, since we want mass of just the solution divided by volume of solution. To get the best value, we measure out 4 different volumes of solution. Because the mass goes up as the volume goes up, the density, which is mass divided by volume, should be similar for all 4 volumes of solution. We add up the 4 density values and divide by 4 to get average density of solution A. We do similar calculations for solutions B, C, D, and an unknown solution. We need to combine our data in a way that makes sense to make a calibration curve. We want to find the correlation between mass fraction and density. Cell A1 in Excel contains my heading, Solution. Cells A2 through A5 contain my solution labels A, B, C, and D. When making a graph in Excel, the x-axis data goes in a column on the left, and the y-axis data goes in a column on the right. In this case, I want mass fraction on my x-axis, so I copy my mass fraction data into my first data column, column B. Cell B1 contains my heading, mass fraction in grams of fructose per milliliter, and cells B2 through B5 contain my example mass fraction data, 0.02618, 0.05102, 0.1001, and 0.1405 grams of fructose per milliliter. These are sample data and should not match the data you will be using. I want density on my y-axis, so I place my density data in my second data column, column C. For example, the average density for solution A goes in cell C2. Cell C1 contains my heading, density in grams per milliliter, and cells C2 through C5 contain my example density data, 0.9797, 0.9839, 0.9924, and 0.9997 grams per milliliter. To make my graph, I'm going to select the data that I want with my mouse. I select cells B2 through C5. I'm leaving the headings out of my selection. I go to the Insert tab at the top of the page. I select Scatter Plot, the one with the dots, and when a set of options pops up, I choose the one with just the dots, no lines yet. That creates my graph. Next, I want Excel to fit my data to a linear equation, so I right-click on one of the dots on my graph and move my mouse down the list of options to add trend line. In the dialog box that opens up, linear is already selected, so I leave that alone. I check the bottom 2 boxes, display equation on chart, display R-squared value on chart. I hit X to close the dialog box. I now have a line that is fit to my data along with the equation for that best fit line and R-squared value on my graph. Sometimes I want more digits to be displayed than what Excel gives me. I can right-click on my equation and select Format Trendline Label from the list of options. In the dialog box that opens up, under Category, I select Number. This allows me to choose a number of decimal places to display. Let's say I want it to display 5 digits after the decimal. I will type in 5 where it says decimal places. I make sure to hit Enter so it makes the changes on my graph before I hit X to close the dialog box. That gives me plenty of decimal places for significant figures purposes. In order for my graph to communicate useful information with other scientists, I need to have everything clearly labeled. Other scientists need to know what each axis represents in order to draw conclusions from my trend line, equation, and R-squared value. I need to label each of my axes, and I also need to give my graph an overall title so that someone glancing at it will know whether the graph is relevant to them. First, I need to click anywhere on my graph. That will bring up 2 new tabs at the top of Excel, which are under the broad category Chart Tools. I want to select the tab called Design, which will be the second from the right side. Next, I want to click on Add Chart Element at the top left of Excel, and select Axis Titles, then Primary Horizontal. My X-axis now has the label Axis Title. I want to change it to a more informative name. I select the letters that say Axis Title with my mouse and type in my new title, mass fraction in grams of fructose per milliliter. I click on Add Chart Element, then Axis Titles at the top of Excel again, this time select Primary Vertical. My Y-axis now has the label Axis Title. Again, I select the letters that say Axis Title with my mouse. And type in my new title, density in grams per milliliter. Next, I change the title on my graph. I select the letters that say Chart Title with my mouse and type in my new title, density versus mass fraction. I can change the font size for the whole graph. I right-click inside the graph. I select Font. I type in 18 and hit OK. I drag the corner of my graph so that my graph is a more appropriate size. I can readjust my equation by clicking and dragging it so that it's not so close to the lines on my graph. My graph is now informative and easy to read. Since the trend line on my graph is linear, the equation on my graph is in the general form y equals mx plus b. M is the slope of the line and is the number to the left of the x. In the equation on my example graph, my slope, m, is equal to 0.17486. B is the y-intercept and is the number to the right of the x, including a minus sign if present. In the equation on my example graph, my y-intercept, b, is equal to positive 0.97503. The R-squared value tells me how well Excel's line fits my data. Since I have fit my data to a linear trend line, it is telling me how close to perfectly linear the data are. The closer the value is to 1, the better the fit. Since you will be working with real data, you should not expect your value to be exactly 1. It may be slightly less, like mine, which is the 0.99983 shown on my graph. Once you find average density of the unknown solution, you can plug that value in for y in the equation for your calibration curve. We plug it in for y since our graph has density on the y-axis, due to it being the dependent variable. We need to rearrange the equation to solve for x, which is the mass fraction of the unknown solution. Notice that we have mass fraction on the x-axis because it is the independent variable. Let's say our unknown solution had an average density of 0.98562. In my example calibration curve, my equation is y equals 0.17486x plus 0.97503. I plug in my density value for the unknown and get 0.98562 equals 0.17486x plus 0.97503. To get x by itself, I subtract 0.97503 from both sides and divide both sides by 0.17486. My rearranged equation becomes x equals 0.98562 minus 0.97503 all over 0.17486. And I get 0.060563 grams of fructose per milliliter of solution as the mass fraction of the unknown solution.